Disks with triaxial dark matter halos.
What I decided to tell you about was some work I've been doing about disks and triaxial dark matter halos, and also to review a little bit of this topic, since this is a vast topic. The reason why this is a vast topic is when we look at cosmological simulations, purely collisionless simulations of dark matter only. An example is shown here. What we find is that the dark matter halos that form are not spherical, they are triaxial. That means that each of their major axes have different lengths. So this was known already, for example, in Frank et al. In 1988, when they measured the shapes of their halos, their axis ratios. A spherical halo would be one that's in this corner. This is 1-to-1 on one axis and 1-to-1 on the other axis. And you can see that in their distribution of halo shapes, very few halos actually approach the spherical systems. And typically what you actually find are things that are prolate, cigar-shaped, and triaxial. The typical measurement was done in 2006 by Brandon Allgood, quantifying how the shape of the halos depends on the mass of the halo. And there is a relatively weak dependence. The minor axis to major axis ratio is scales as m to the power of minus 0.05. So it's a relatively weak scaling. It will depend it will change on orders of magnitudes of scales of the halos. On galaxy scales, we expect that the typical axis ratio will be something like C over A of 0.4 and B over A of 0.6. Now, I'm going to show you a little bit of observational results, but to give you the conclusion already in advance, when we try to measure the shapes of halos observationally, and this is a very, very hard thing to do, what we typically find are that halos within the regions within which we can measure them are oblate. They have axis ratios of B over A of about 1, so equal a major and minor axis, and major and intermediate axis, and C over A of about 0.8 or a bit more. So relatively close to spherical. Certainly not these kinds of numbers you're seeing out there. And I'll explain why we think that happens in our current understanding of galaxy formation. But just to show you some of the effects that you might expect from a triaxial halo, from a disk sitting inside a triaxial halo, here's an example of a disk sitting in such a halo. And the orbits that you end up getting in a system like this are not circles. The closed orbits are not circles, they're ellipses, and that's what you see over there. You see something that's elongated. And if you measure the tangential velocity, v phi, that's what's being plotted there, as a function of position, you find that along the minor axis of the disk, you have velocities of order 300, and along the major axis of the disk, you have velocities of a smaller magnitude, about, let's say, 200. And that's a factor of about 30% difference as you change from one position angle to the other. And that's simply because stars here are not on purely circular orbits, they're moving on ellipses. So there is associated also with this elliptical motion, there is also associated a radial motion. That's what we see on that. It's worth mentioning that in a system like this, the major axis of the halo is horizontal, it is not vertical. So the disk gets elongated perpendicular to the elongation of the halo. So the net potential ends up being somewhat rounded. Now this is important, things like this are important because if you were looking at this galaxy to try to figure out its rotation curve, you would make a mistake if you took your slit along there, or along there, or along there. The amplitude of the rotation curve you get would depend on them. And that would lead to scatter and the Tully-Fisher relation. You would have one magnitude for the entire galaxy, but the amplitude of the velocity changes. And this effect actually is made worse by the fact that one of the first things you do when you do rotation curve measurements is try to deproject the galaxy. And if your galaxy is not intrinsically round, when you deproject it, you're going to make some mistake. So you're going to overcorrect it.